Welcome to our Quantum Deep Dive, an explainer based on an essay by Yorgo Ishnepat. Today, we're telling the story of one physicist who built the bridge between an abstract dream and the tangible reality of quantum computing. Today, we're going to explore the story of Isaac Chuang, the physicist who really built that first bridge from quantum theory to reality. We'll track his journey through 5 key stages, starting with the wild theoretical challenges of the 90s, then his unique background, the surprising tool he found, the exact moment it all came together, and finally, the lasting blueprint he left for all of us.
Okay, so let's dive right in. To really get what Isaac Chuang pulled off, you have to rewind to the 1990s. Back then, quantum computing was this absolutely brilliant, mind-bending idea, but it was pretty much trapped on paper. It was a world of pure theory, and it was up against this huge fundamental challenge. How in the world do you build a real computer out of the bizarre, almost nonsensical rules of the quantum world?
Right, and at the heart of that problem is this massive difference between a classical bit and a quantum bit, what we call a qubit. A classical bit is super simple. Think of it like a light switch. It's either on, that's a 1, or it's off, a 0. No gray area. But a qubit is more like a coin spinning in the air. Before it actually lands, it isn't just heads or tails, it's in a state of being both at the exact same time.
And that strange property is called superposition. It's really the secret sauce of quantum computing. Because it can exist in multiple states at once, some combination of 0 times 1, just a handful of qubits can represent and process an exponentially bigger amount of information than the same number of classical bits. This is exactly where quantum computers get their immense potential power. But it's also what makes them incredibly delicate and just so hard to control.
And this brings us to the second key idea, entanglement. And this is where things get even weirder. When you entangle qubits, they become linked in this really profound way. If you measure the state of one, you instantly know the state of the other, even if they're on opposite sides of the universe. Albert Einstein famously called it spooky action at a distance. But for quantum computing, this spooky link is an unbelievably powerful tool.
So you've got these two bizarre, almost magical concepts, right? Superposition and entanglement. Who on earth could possibly build a real working machine out of them? The field desperately needed a bridge builder, somebody who could connect the abstract world of quantum physics with the practical world of engineering. And that's where Isaac Chuang comes in.
Chuang's background was almost perfectly designed for this massive task. He was born in the U.S. to Taiwanese parents, so he grew up with this great blend of cultural perspectives, a deep respect for discipline and analytical thinking from his heritage, mixed with that innovative, boundary-pushing spirit of American society. He was a whiz at math and electronics early on, and then he went on to study electrical engineering and computer science at Stanford, and then got his Ph.D. at MIT. This unique education put him right at the intersection of theoretical physics, computer science, and hands-on engineering. He wasn't just a theorist or just an experimenter, he was both.
He was also massively influenced by the legendary physicist Richard Feynman. Now, while Feynman famously said that nobody understands quantum mechanics, he also threw down this incredible challenge. He argued that if you really want to understand nature, you can't just describe it with math. You have to build a machine that runs on its principles, a quantum computer, to actually simulate it. That idea basically became a guiding star for Chuang. He didn't just want to understand quantum information, he wanted to build it.
So Chuang knew that all the abstract algorithms and equations in the world weren't enough. To build a quantum computer, you need a physical system, a real, tangible piece of hardware where you can create and control these incredibly fragile quantum effects. The challenge was finding the right material, and he found it in a very, very unexpected place.
Yeah, the tool wasn't some exotic, futuristic device from a high-tech physics lab. It was nuclear magnetic resonance, or NMR. This was standard equipment you'd find in any chemistry department, used for figuring out the structure of molecules. Chuang had this brilliant insight that this tech, which uses magnetic fields and radio waves to peek at the nuclei of atoms, could be completely repurposed. He realized he could use NMR to precisely manipulate the quantum spin of those nuclei, and then use them as his qubits.
Now, what's so cool about this is how it all works. You take a liquid with specific molecules and pop it into a powerful magnetic field. Then, you hit it with these carefully designed radio frequency pulses. These pulses are almost like a language. They talk to the atomic nuclei, tipping their spins to create those states of superposition and entanglement. And then, finally, you just listen for the faint radio signals the nuclei give off as they settle back down. That signal holds the answer to your calculation. They were literally getting atoms to do math.
Okay,
So Chuang had his qubits, the atomic nuclei, and he had his tool to control them, the NMR machine. Now came the ultimate test. With his team at MIT and later working with IBM, Chuang set out to do something nobody had ever done before: run a meaningful quantum algorithm on a real quantum computer. This was shaping up to be the field's Sputnik moment.
The big question hanging over the entire field was this: could these unbelievably fragile quantum states be controlled with enough precision to actually run a famous algorithm and get a real answer? Or would the tiniest disturbance, what physicists call decoherence, just destroy the whole calculation before it was even finished? Proving this was possible would finally yank quantum computing out of science fiction and into the world of hard experimental fact. The target for this historic test wasn't some impossibly complex problem. It was a single, simple number, 15. Yep, 15. The challenge? Make a quantum computer find its prime factors, which of course are 3 and 5. Now you might be thinking, that sounds trivial, but factoring huge numbers is one of the hardest problems for classical computers. It's the entire foundation of modern encryption. The goal was to run Peter Shor's amazing quantum algorithm, which promised to do this exponentially faster than any machine we'd ever built. And in 2001, they did it. Using a custom-designed molecule inside a 7-qubit NMR machine, Chuang and his team successfully ran Shor's algorithm and got the right answer, 3 and 5. The results were published in the prestigious journal Nature. This was it. This was the proof of concept the world had been waiting for. It was a monumental achievement, showing for the very first time that a quantum computer could solve a problem that showcased its unique power. The entire field was changed, forever.
But here's the thing. Factoring 15 wasn't the end of the story. In a lot of ways, it was just the beginning. Chuang's work wasn't just about one single experiment. It was about laying the foundation, about creating the entire blueprint for the field of quantum information science that would come next.
His legacy is just incredibly broad. Besides pioneering the first working quantum computers, he co-authored the definitive textbook on the subject. It's still known by students everywhere as Mike and Ike, and it really is the Bible for anyone getting into the field. He also did critical work on quantum error correction, built a world-class lab at MIT, and maybe most importantly, he mentored a whole generation of scientists who are leading the quantum revolution today.
So the crucial point is this: his work is the bridge between two completely different eras of quantum computing. Back in the 90s, the big question was, can quantum algorithms even be physically realized? Chuang answered that with a resounding yes. Today, the challenge is all about scaling up, about building a real quantum industry. And here, too, his contribution is vital, because he provided the foundational textbook, the academic standards, and the trained experts we need to tackle these new challenges.
He was the architect. He built the bridge from abstract theory to physical reality, proving that this radical new type of computation was actually possible. Now that that bridge is built, the question for all of us has changed. It's no longer if quantum computers will change our world, but when and how. Which leaves us with a final thought to chew on. If you had a powerful quantum computer right at your fingertips, what problem would you solve first?
We'd really like to thank Jorg Oa Schneppat for the source material for today's deep dive. His detailed essay really provided the blueprint for this entire explanation.
Thank you for joining us on this deep dive. For more insights and to read the original essay for yourself, be sure to visit schneppat.de. Goodbye.
Schneppat.de is a private project by Jorg Oa Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.